All right, so here we go. Pendulum. You know what a pendulum is, right?
C. We got two. It's
All right. And you swing back and forth.
I need a straight edge.
All right.
Why is he hanging from his head?
It's a monkey. An execution.
It's a noose.
You may see a noose. I see Tarzan swinging about the neck. All right. So here we go. Swings back and forth. Will you please, at location number 1 down here at the bottom and location number 2 over here, will you please draw the free body diagram? Free body diagram, everyone.
We out of town.
When you're here, we have a force downward and a force upward. Did you think enough to draw them proportionally?
Yes.
Which one's bigger?
Tension.
Tension is bigger. Very nice. Tension is bigger, but why is tension bigger?
Because the person's moving upwards.
The person's moving to the left.
Centripetal acceleration.
Because. Now remember, the direction something moves does not tell you which way the force is bigger. It's the way it's accelerating, right? So the deal is right here at this instant in time, the person is moving, if I draw it this way here, so there's no confusion, moving to the left. The velocity of the person is this way, right there. But the acceleration of the person is this way. Very good, because by now we ought to be able to spot whenever something's changing direction, you have an acceleration. And you're accelerating towards the center of the curve. Yes?
Well, like, hold on, finish. It's relative, but it's like inverted. Go ahead.
Relative but inverted.
Well, like, what if, okay, like you have a pail of water, right, and you're spinning it around in a circle.
Mhm.
What if it was up at the top?
Okay, if the person was up at the top, that would be painful. All right, there would be a tension down and an mg down. Which way would the person be accelerating?
Down.
Downward.
But which force is bigger?
We don't know.
Okay.
Because F equals ma, these two add up. T plus mg equals mac, or mv squared over r. The deal is that this one can't change. So the one that will vary is tension. So the slower you go, the smaller this gets. The faster you go, the bigger that gets, until tension either breaks if you go too fast, so the tension breaks meaning the strings breaks,
Or the person lets go.
or, yeah, true, person lets go, or if you're going slower and slower and slower, how slow can you go?
Zero.
Until this becomes 0, and when that becomes 0, notice what happens. This goes away, and we're left with mg equals mv squared over r. The m cancels out, and we're left with the centripetal acceleration equals g. That's the minimum v squared over r you can have. This is the minimum velocity you can have, or otherwise you're no longer in circular motion, you're now in trajectory motion, and you fall out of the curve. Remember that from circular motion?
I do.
That's what it does.
All right.
Do you think?
Okay, I guarantee you on the test somewhere there will be some sort of changing motion on the exam to see if you spot the centripetal acceleration. Okay, it's always on there.
And there's always centripetal and pendulums.
And there's always what?
There's always centripetal motion and pendulums.
There's always centripetal motion in pendulums at certain spots, okay? Because here's what I want to talk about. When we get over here, I'm going to draw this one nice and big over here. When the person is over here, you have tension and you have mg. But when you're out on the end, okay? When you're out here on the end, what's your velocity? Your velocity is 0.
Why?
So are you traveling in a circle at that spot?
Wait, why?
Are you?
We're in rotation.
You're momentarily stationary. Very nice. So is there a centripetal acceleration?
No.
No. So which way are you accelerating?
Down.
Down.
Straight down?
Yes.
Yes. Well, you're not.
No.
But you have these two forces. Which way do they add up?
Oh, wait.
To the right.
It's going to be somewhere in here, and you can tell exactly where the acceleration points. If you think about it for a second, when the object swings out here, okay, swings all the way out here, think about it. If you're at rest and then you start to move that way, which way are you accelerating? That way. If I'm at rest and I start to accelerate that way, sorry, if I'm at rest and I move that way, then which way am I accelerating?
Wait, how can you be at rest and you move?
I'm at rest and then I move.
And then I move.
So which way am I accelerating? That way, right? Okay, here's the deal. If something's at rest, it's easy to spot which way the acceleration is going to be because it always points in the direction of where it moves to next, right? Where does this move to next?
Down a little to the right.
Yeah, it moves tangent to the path, right? It's going to move back this way. So the acceleration at this point is going to be this way. And it's not centripetal because there is none. So if it's not centripetal acceleration, what's the other kind of acceleration? Tangential. Okay, so here's the deal. As we go along this thing, back and forth, we oscillate between completely tangential at the ends and completely centripetal here, and then completely tangential over here.
But the minute it starts to have velocity again, then it's...
All right, so let me draw several pictures. Here it is going through the motion.
That's not proportional.
All right.
It's losing mass.
It is.
We've said... Wow, it is losing mass. All right, so right here we said we have centripetal acceleration only. Over here the centripetal acceleration is 0 and the centripetal acceleration equals 0. Right here we have no tangential acceleration. Right? It's not speeding up that way or that way, right? Tangent to the path. But right here it's all tangential. Tangential, tangential. Okay, right here, is it changing direction?
Yes.
Yes. That way, right? And right here. Right here, is it changing speed?
Yes.
So it has tangential. Which way is it changing speed?
To the right.
Tangent to the path, that way, right? Because here's our path, right? So this way. All right, so what we end up with is a complete and total acceleration of this. Here's my total acceleration. Here's my total acceleration.
Oh my gosh.
Here's my total acceleration.
It's much better.
Here's my total acceleration. And here's my total acceleration. So what happens is it does this. It goes from this to this to this. See? It goes like this to that, and back as it goes back and forth. That is nature's acceleration. We split it up into tangential and centripetal because it's easier for us to figure. Okay?
It's kind of like your little. Okay, you probably haven't done this, but when I was at the skate park with my friends or whatever, we were rolling, like trying to roll each other on the
Yeah.
little thing.
The tube
So
or
we started off like
half pipe or whatever.
down or whatever, and then so when we went that way, we would like end up at the very bottom, but we push ourselves to where we, I don't know. It was like
Did
you're
you
rolling
just get
back and forth.
Right.
Physics purposes.
Actually, yes. If you're at, this is the same thing for pendulum, then it would be the exact same thing for a skateboard park.
That makes for a pretty cool problem.
It's the exact same
The
thing.
pendulum like shoots it off with something there and then it falls onto the tube.
Because here it's tension and gravity, here it's gravity and normal. But they're exactly the same orientation, so it's exactly the same. All right, so there you go. That's a little craziness with pendulum motion as the acceleration goes back and forth. Now remember, you're looking for two things when you look for acceleration to help us out. We're looking for, is it changing direction? That'd be centripetal. Okay, now remember, changing direction like turning, right? All right. And it has to be moving to have a centripetal acceleration because it's v squared over r. The other thing is it changing speed? So changing direction and changing speed, those two things, right? And those add up to give us our centripetal and tangential acceleration, which we combine to give us the real total acceleration, okay? Nature's acceleration. All right, blah, 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 yada, yada, yada. Okay, the only other thing I wanted to say about pendulum motion is this. We're not going to derive this. I'm just going to give this one to you. Tension equals 2 pi square root of L over G, where this is the length of the pendulum and this is the mass of the pendulum, and G, of course, is G. It turns out that M cancels out when you work this problem. M disappears, and you get this. Now remember that time period equals 1 over the frequency, right? So that's 1 over the frequency equals 2 pi square root of L over G, right? Sorry, that looks like an E. That's L. But what's frequency equal to in omega?
Omega over 2 pi.
Yeah, omega.
Frequency equals omega over 2 pi.
Okay, because omega equals 2 pi frequency, right? Is that right?
Yes.
So frequency equals omega over 2 pi. So let's change that and put that in here. So really that goes in as 2 pi over omega equals 2 pi square root of L over G. The 2 pi's go away. And so what is omega for a pendulum? Square root of G over L. Okay, just like remember for a spring system, for a spring mass system, we found out that omega equaled the square root of what? M over K or K over M?
It equals square K over M.
Okay, think about it for a second. Frequency is how, angular frequency is how fast it's going back and forth in rads per second, right? So if the spring constant goes up, should this be faster or slower?
Slow.
If I have a little bitty spring like this, and a mass, or a big spring and the same mass, which one will go back and forth faster? The small one?
If I compress it the same amount,
Which one's going to apply the bigger force when you compress it? The big spring. So therefore it'll push it faster, right? More force, more acceleration. Okay, so K must go in the numerator. And in the denominator, mass. What if I have this spring, same spring, and I have a little mass and I have a great big mass? Which one's going to go back and forth faster? The small one. That means as mass goes up, omega goes down. So therefore it has to be in the denominator. Does that make sense? You can always figure it out. Just think about it. Okay, just reason it out. You know it's got to be M and K, but which one? M over K or K over M? Same thing here. G over L. Omega is G over L. So in order for this to go faster, if you take this to a bigger planet with a larger gravitational field, it'll go faster. It'll swing back and forth faster. You take it to the moon and it swings slower. You take it out in orbit,
It's just chilling.
it's just chilling. Very nice. Okay, and the length. You have a little bitty pendulum or a really long pendulum. Which one goes faster? Little bitty one. The big one, real slow.
we got one.
If you don't believe that, just try it. Try it.
We're gonna go out and get a little pendulum and a big pendulum.
Oh. Pendulum. Right? You ready? Long pendulum.
Whoa.
Okay? And now, little bitty pendulum. Much faster, right? That's adorable.
I love
That should have been recorded.
high pitch.
Ultimate power.
Watch this little short person coming in like,
Yeah.
Okay, now it's time for us to talk about the really incredibly crazy problem that they gave you on the last year's exam that almost no one in the nation got right.
The spring one?
No,
I bet the person who wrote it must be very proud.
I know.
No problem.
In fact, I talked to my students last year about this and I said, but don't worry about it. I'm not going to derive it because they won't expect you to derive this on the exam. And guess what? Question number 2. Derive this. And I'm like, oh no.
Oh no.
Oh no.
That could explain so many of the things in history.
Okay, physical pendulum. Okay, what a physical pendulum is, okay, simple pendulum, this is a simple pendulum. Okay, where it goes back and forth, and you have all the mass at the end. All the mass at the end. Okay, a physical pendulum then would be like this, where you have where this has mass, and this has mass. And guess what one of the questions was on the exam? Find the center of mass, I think was one of the questions. I don't remember if that, but I know one of the questions was find the moment of inertia. So let's do that quick. Where's our pivot point? Right here. Our pivot point is on the end. So assume this to be a uniform bar. Let's say this has a mass of m and this has a mass of m to make things easy on us, okay?
But it won't be easier.
Actually, no, let's make it more realistic. Let's make this 2m and make this 3m, just because. Because we can do that. All right, so our moment of inertia then
Is
is
that a disc or a ball?
moment of inertia for the entire thing, this thing, equals the moment of inertia of this thing plus the moment of inertia of this thing. Right? Okay, so what's the moment of inertia of this bar? Let's have it at a length of L.
1/3.
Is it 1/12 or 1/3?
1/3.
1/3. 1/3 because we're about this pivot point right there. 1/3 ml squared. But what's our m? 2m. So this is 2/3 ml squared when you put in the actual mass. All right. Now, what's the moment of inertia of that?
Disc or ball?
Is there a disc?
Ah.
Make it a sphere.
If we really want to be ugly, we could make it like a sphere and give it a radius, right? So we could. But let's just assume it to be, okay, let's assume it to be a sphere.
Wait, can we do lumpy mass?
Let's make it a sphere of radius r.
You're a lumpy man.
Sphere of radius r.
Is it hollow or solid?
Good question. Solid. Okay, so for this one then, what we have to do is find the moment of inertia of this about its center of gravity plus an md squared, right?
Yeah.
So that is going to be, what's the moment of inertia of the sphere itself?
2/5 ml squared.
2/5 mr squared, right? 2/5 mr squared, but 2/5, but our mass is 3, right?
Yeah.
So it's going to be what? 6/5 mr squared. Yes,
What's
ma'am.
that symbol next to the I?
That symbol right there is the moment of inertia of the sphere about its center of mass. But then we have to move it out to this point, right? So this is going to be 2/5 mr squared plus ml squared in our case, right? The parallel axis there. Remember to move it off that spot.
Or would it be
Because is it rotating about that spot?
Mr. Bruin, it's,
Right?
it's unfortunately L plus R, right?
Yeah, L plus R.
Because of the radius.
Ah! L plus r
Probably be squared.
squared.
That's
Oh my,
kind of
Janice the Two-Face guy.
All right, so it's going to be 3m times, because it's 3m, right? 3m L plus r squared. All right, now you can do some mathemagics if you'd like and try to simplify that, or you can just leave it.
Did you say mathematics?
I did. It's magical.
I just tried to win.
All right, so there you go. Ugly, ugly, ugliness.
We should like
Okay,
expand it. Oh, but no.
from here on out, we will refer to this whole thing as I.
I.
Okay? Everybody okay with that?
I.
All right.
A-Y, brother.
Yes, somebody had a question. Somebody had a question? All right, yes.
Your answer?
No more answer?
Any? Go ahead. All right, so here you go. Now, what we have now is this problem. Let me draw this in black. So here's our problem, is we have this pendulum that has a center of mass somewhere here and a moment of inertia of I. You know what? We do have to find the center of mass, don't we?
Yes.
Rats. Okay, let's find the center of mass of this system, please. Where from this pivot point, measured from here to here, down this way, starting from here, where is the center of mass for the system? Or for the combined object? Okay? Now, it's at an angle on the board, so let's make life simple on ourselves, and let's do this. Here's our problem right here. And here's the center of mass of each part. This center of mass right there is at a distance of L over 2. This center of mass right there is at a distance of L plus R. Right? So to find the center of mass, location of the center of mass, the equation is, do you remember?
Sum of MRs.
The sum of the MRs over the sum of the M's,
I
right?
actually knew that.
Because the way I think about it, it leaves you with an R.
That's correct. It has to leave you with R, or meters, right? So, MR, because you have to have mass and location, and you got to divide the mass out, right? The total mass. All right, so, this first one, what's the mass of the first one? 2m, and its radius is L over 2. Plus, what's the mass of the second one?
L plus R.
3m, and its length is L plus R.
Is there a way we can relate length and R? Like
No.
Or
R is
can we
like,
define it just for
I think on the test they did. Actually, I think on the test what they did is they did not have a radius for this. They just had what they considered to be a point mass, probably. I think. Or they gave you,
Or it wasn't
I don't remember. Or it wasn't a sphere, I don't remember. And anyway, that's our total mass. 5m. Okay, so that's how we would figure out where the center of mass is, right?
Yes.
Okay, now this is harder than the one they had on the exam, because theirs kind of factored to, I mean, that you were able to add some of these things together. I don't think there was this R in here, or the R was related to L, so it all kind of condensed a little nicer. Okay? All right, so why do you need to know those two things? Where the center of mass is and what the moment of inertia is. Here's why. Because here's the way this thing works. There's the pivot point, and here's mg for the entire thing, right?
Yes.
5 mg.
And here is the radius to this point. This radius is the distance to the center of mass, right? Okay, from the pivot point.
So then you would have to find everything from there.
All right, so here's how this works. Here's the math behind it. You ready? The sum of the torques equals I alpha about the pivot point. Okay? All right, so what is the torque right now? What would I put here?
R cross
It's R cross mg, right? But what's our R?
R center of mass.
Is R.
Distance.
Our mg is mg, but the cross is going to be what?
Sine.
Okay, here, that's this theta right here, right? Which is the same as this theta here, right?
What are you?
That's right? Because this points in this direction, this points in this direction, this is the direction between the points.
Oh, okay.
So that's sine of theta equals I alpha. Now, I'm going to have to do one thing, okay? And here's the thing we're going to have to do. Is we have to put a negative sign in here. Okay, and the reason why is because the torque decreases the angle theta. Okay? The torque decreases the angle theta.
Is R the center of mass?
But it also makes sense. Like, you look at the side of that angle.
Is R what?
The length, or the center of mass?
R, that's correct. This R is the distance to the center of mass. So if you want to put that in there, that's cm. radius to the center of mass, okay? If you'd like. I'm going to drop that probably, so I don't want to keep writing it. But all right, so now here's what we're going to do. This is what's called the small angle assumption, because we cannot go much further with this unless we assume something fancy. So we will assume that theta is small, therefore sine theta is approximately equal to theta.
Hey, but when,
Yep.
how can you, okay,
How can we do that?
like, that's not all,
That's correct. What is considered small?
Less than
Call it small angle.
We'll call it.
Get your calculators out. Everybody? Take the sine of 5 degrees. Because what's the sine of 0? 0. So what's the sine of 5 degrees? 0.09. I think that's small. Okay? What's the sine of 10 degrees? That's 0.17. Okay? What's the sine of 20 degrees? That's 0.34. Okay, now what's as big as sine theta can get? 1, right? Okay. What's an acceptably small amount of error?
10%?
Less than 10%? The answer is it's acceptably small whenever it doesn't screw things up, quite frankly. For engineering, that's the way it works. We assume things are small all the time so that we can solve stuff, but then when we actually build a computer model for it, and then we predict with the computer model, and then actually do the thing in real life and find out that our model doesn't match, we go back and we put things in that we may have assumed small that really aren't small, and we keep building them back up until we kind of get we get an acceptably easy to solve equation for an acceptable prediction of the real world.
That's kind of scary.
Okay.
Like sine of 5 is like 0.
Okay, now we have to do this in radians. Okay, let's go back. Let's go back and do this in radian mode so it'll make more sense. Go to radians, select radians, and then go, okay, what's an acceptable... I can't think in radians is my problem.
Power over 30.
Pi, oh man.
So 180 divided by what? It was going to give you 5. What do you do?
34.
Pi divided by 60 is 3 degrees.
Why don't you just,
Yeah.
What did I say?
Sine of pi over 30 is power.
Okay, so pi over 2 is 90, pi over 4 is 45, okay? If you go to 45 degrees, you're going to get quite a bit of error. Okay, if you go to 45 degrees, you get 10% error, okay? All right, so 10% is a lot of error, quite frankly. Generally, we consider small angle as if you have less than 5% error. So how far do we have to go? Let's see, pi divided by 8.
180 divided by 8.
Okay, that's 3% error. So what's that, 20 degrees-ish?
22.5.
All right, so let's just say this. Around 20 degrees or less, you would get less than 5% error. I think it's if you're under 10% angle, you get less than 1% error, if I remember correctly. Okay? So around a 20-degree angle, which is a relatively good size angle, you would have less than 5% error. About 4% error, somewhere in there. Okay? All right, so that's a reasonable range where you could have this thing moving back and forth and it wouldn't make any difference. All right. There's actually a lot of things like that. We used to do that in Bell Helicopter all the time. If we assume that to be small, our equation becomes negative r mg theta equals I alpha. Okay, so here's our first assumption. Assumption number 1. Now we're to the, do you remember stage? Okay?
No.
All right, what is alpha?
Yeah.
A over R.
What's alpha in terms of theta?
Unknown. That's a good question.
Because remember, we kind of did this when we did drag, right? We had A and V, acceleration and velocity, in the same equation, so we related them by making A equal to what? dv dt, right?
Yes.
So how do I relate alpha and theta?
Theta equals theta squared.
It's d squared theta over dt squared. So I'm going to plug that in. So that becomes negative rmg theta equals I d squared theta dt squared. All right, next thing to remember is, do you remember when we had simple harmonic motion, when we had d squared x dt, that equaled negative omega squared x? Do you remember that? Oh, thank you. When we had simple harmonic motion, we had acceleration equals the second derivative of displacement, and that equaled this, right? We end up with negative a omega squared cosine theta, cosine omega t, right? And we said, but wait, look, that means acceleration is negative the displacement times omega squared, right? So what? How could we do that same thing in this form? D squared theta over dt squared equals what?
Negative omega squared
Negative omega squared
theta.
theta, right? Negative omega squared theta. So I'm going to plug that in right here. So that becomes negative rmg theta equals I times negative omega squared theta. Okay? Theta goes away.
Bye-bye, Theta.
Bye-bye theta. And my negative goes away. And we're almost done. Will you please solve that for omega? Omega equals what?
Square root of RMG over I.
Square root of RMG over I. Right?
The negative.
Negative went away. Now, everybody, this is the moment of inertia about the pivot point. And this is the radius from the pivot point to the center of mass. So RCM. Now, in a lot of books, they'll just call that D. So if you want, you can just call it D if you want. The distance to the center of mass, if you'd like. Same thing. Okay, now we got one last step. What's omega equal again?
2 pi.
Yeah.
In time period, what does it equal?
2 pi over time. Period.
This equals 2 pi here. So remember that omega equals 2 pi over time period. This equals 2 pi over time period equals the square root of R, center of mass, mg, I, pivot point. Okay, will you please solve that for t? Because we want to make this a time period equation just like the time period for a simple pendulum. For a simple pendulum, time period is equal to 2 pi square root of L over G.
Oh, would it be 2 pi square root of I over R?
So it is
Sorry.
t equals 2 pi square root of I
Over RMG?
over RMG. And that's the R to the center of mass, right?
And then you can, I equals, well, you can cancel out the R's.
Ah, now, if you know what the moment of inertia is, you can plug that in, like all this
Oh, and the N.
stuff. And then if you put in what the R is, which I erased, our center of mass radius, right? You plug that in. Okay, now let's do what we call an idiot check, right? So if we go back to a simple pendulum, does this work? Here's our simple pendulum, right there. Okay, our simple pendulum, this is the distance to the center of mass is L, the length of the pendulum, right?
Yes.
And what's the moment of inertia of a simple pendulum?
ML squared.
It is mr squared, right? Our mass is m, and our radius is L squared. So let's plug that in and let's check. So if I plug that in, I get 2 pi square root of ml squared over L mg. What does that become?
L over G.
Haha, it becomes 2 pi square root of L over G, which is a simple pendulum.
Yes.
So this is really the more accurate equation for any pendulum. If it happens to be a simple pendulum, then it turns out to be that. Okay? So actually, we did derive the equation, didn't we? So there you go.
Cool.
Now, if on the AP exam they ask you to derive something like that and you're really lost, or you realize that it's going to take you an incredible amount of time, you got a couple options. Number one, leave it to last, okay? And then do it last if you can. But if this is part B of the problem, and then you have C, D, and E afterwards, where you need to know some of this stuff, that's a problem, right? Now, what they've done on most exams, when they have you derive stuff like this, not most exams, some exams, what they'll do is they'll say, show that the time period for a physical pendulum, or for this pendulum, whatever it was, is this. Okay? And then you have to derive it. So you have to work towards what you know the answer is already.
It's like a proof.
Yeah, it's kind of like a proof. Prove that this is true. If they don't have the proof one, where they just tell you, okay, look, you have to derive this, what is it? And if you're really stuck, you're right. You make an assumption and you go on from there, right? Because you can't let that ruin the rest of your exam if you're really stuck on it, okay? All right, so there you go. And if you have time, you can go back and fix it. I suspect that most of you, given enough time, and all of you, given enough time and resources, could figure this out, right? When you're out in your career later in life and you're required to figure something like that out, I have full confidence that all of you can figure that out, okay? It's just that you might have to ask someone for assistance, or you have to look something up in a book, right? Because you have all these things at your disposal in the real world, right? But on the test, you got to do what you can do, okay? Which is one of the bad things about the test, is that little business. All right, so we got to do gravity now, so let's move. There are 4 forces in nature, okay? Excuse me. There are 4, count them, 4 forces in nature, at least at the energy level at which we live. At the temperature where we live, there are 4 forces only. You can describe all forces with these 4. And they are, what are they? Gravity. Electromagnetic.
Weak nuclear.
The weak nuclear and the strong nuclear force. Now, the weak nuclear force and the strong nuclear force. Okay, the strong nuclear force is the strongest. The strong nuclear force acts over a distance of about that far, except it's smaller than that. Yeah. Okay? It only acts at nuclear ranges for the most part. Okay? So in our world, in our existence, we don't experience it. Okay? It's happening inside of us, but we don't experience it on a daily basis. Okay, the weak nuclear force is not the weakest force. It is number 3 of the 4. Okay? It too acts over a short distance, I believe a little bit longer than the strong nuclear force. And so when the nucleus gets large enough, it tends to overpower the strong force, and the nucleus tends to break down. Okay? But once again, it acts over such a short distance that we don't experience it in our lives. Okay? So the only two that we experience in our lives are the electromagnetic, which extends to infinity, and the gravitational force, which also extends to infinity. Now, the electromagnetic force over large distances tends to cancel itself out, even though it's ranked number 2 on the which is the strongest list from top to bottom. Strong nuclear force is the strongest. Electromagnetic is second. The weak force is number 3. And gravity, by far, is the wimpiest of all the forces. But over large distances, gravity reigns supreme because gravity only attracts. The electromagnetic force tends to cancel itself out over large distances simply because most things are made up of both protons and electrons. And so right now you're being pulled to the Earth with an incredible force because all of your electrons are attracted to the Earth's protons. And much worse, all of your protons are attracted to the Earth's electrons. So you're being crushed down. In fact, if gravity was as strong as the electromagnetic force, you'd be about that tall. The width of a sheet of paper. It's like a billion times stronger than gravity. All right? But all of your electrons in the Earth electrons repel, and all of your protons in the Earth protons repel, so it all cancels out nice and beautiful. So we're not propelled off the Earth nor crushed to the Earth by the E&M force. Okay?
So
Gravity, on the other hand, only attracts. Yes?
So we're missing a few electrons, we would experience electromagnetic force.
Yeah, that's correct. So like, for instance, if you could like rub a cat on the Earth and rub a cat on you, so you and the Earth have the same net charge, we could send you into space, you bet.
That'd be much cheaper.
Because cats are awesome for generating static electricity. I own 2 cats simply for this purpose.
That's how we're going to solve all the Earth's problems.
So you can throw them from their ankles and they land on their feet.
I love cats. I take a cat and rub a balloon on one cat. Oh, actually, I take my cat and tie it to a string. I take my other cat, tie it to a string. I rub a balloon on both of them, and then they go, woo. Oh, I'm sorry. I do that to the balloons, not the cats. That's right. Yes. Now, gravity rules supreme in the universe simply because it acts towards infinity and it doesn't cancel out. So as you move away from things that have plus and minus charge, they tend to cancel each other out. And you end up with this gravity force, even though it's really, really, really small. It's enough to govern the destiny of the universe, okay? By the way, now they think, like when I was younger, they thought the universe might go out because they had discovered back, shoot, when was it? In the 30s or something, I don't remember when it was. Hubble discovered that the universe was expanding.
Oh, this was a question on that physics
Yeah.
SAT test.
They assumed they found the universe was expanding by the red Doppler shift.
Yes.
Okay? And then they thought, well, but the universe has gravity, so gravity should be slowing it down. And from their early predictions, they said, yeah, it's slowing down. So they were worried about the universe going out, stopping, and then recollapsing. The Big Bang and the Big Crunch, they called it.
The big crunch.
And then, the more they studied, they weren't sure if it was slowing down or not. And they thought, well, maybe the universe will go out to some spot and stop. The Goldilocks theory, that it was just right. Just enough mass to stop it, but not too much mass to make it crunch. And now, they believe from the latest measurements, just from the last 3 or 4 years, I think it is, that they believe that the universe is not only expanding, but its expansion rate is accelerating, and they don't know why. Who knows Tycho Brahe, or Tycho Brahe? Anyone?
Not personally.
He was back in the 1600s? He was an eccentric, very rich guy who had a telescope. And he liked to look at the stars and take intricate measurements of where the planets were and all that stuff. Okay? And you've heard of Johannes Kepler?
Yes.
Okay, by the way, Tycho Brahe was really interesting. He was in a sword fight, and he got his nose cut off.
What?
And he gave it to his girlfriend, I think.
No. And back then you didn't have like plastic surgery. So he had a silver nose made.
That really sucks.
And he wore a silver nose.
That's kind of gross.
Yeah, you can get a silver.
Hey, it's not any different than people with gold teeth all the way across the front.
That's ghetto. They do that on purpose.
Hey, his nose is just there.
Yeah.
That should be the new thing.
I'm going a grill for your
Well,
nose.
you can start it. We can get you some pieces of
Anyway, Kepler, mathematician mostly, pseudoscientist a lot. A lot of Kepler's stuff was total hogwash. Okay, I know, but Kepler was a brilliant mathematician and wanted to study Tycho Brahe's information, and Tycho would say, he said, no way. So
What's Kepler's
Kepler
law?
goes, you know what? Can I work for you and help you take the measurements? He goes, sure.
And he stole it.
Yeah, he waited for Tycho Brahe to die and then he stole it.
That's
Really?
genius.
He stole it, and then from that he,
Well,
Kepler
Tycho's not
was,
gonna use it
that's
anymore.
right, he's dead, along with his silver nose.
His silver nose died a long time ago.
All right, Kepler discovered these things. Kepler discovered that the planets are in elliptical orbits, that the planets swept out equal area in equal time. That means this,
Crazy.
that not only are the planets doing this, but they don't move the same speed the whole time. He said that in any given time period, say this is 1 year, that this planet would sweep out from there to there, and this area, but when the planet was over here, it was here and went to here in 1 year, and this area here would be the exact same as that area, which meant that it travels faster here and slower here. Now, today we have lots of ways of explaining that, but back then that was really impressive. And to discover that just from a bunch of measurements on where the planets are, it took tremendous geometry to figure that out.
He's a TI-1.
Yeah, he used to TI-1.
Hey, I've used a TI-1 there.
Okay.
Born in 1600s?
Mr. Carter's really old.
No, try 1960s.
All right.
It's pretty fun.
Kepler also discovered one last thing, and that is that the time period of the orbits was equal to, the time period squared of the orbits was equal to some constant times the radius of the orbit cubed. So that all the objects orbiting the Earth could be related by this thing with one constant for all the planets orbiting the Earth.
That blows
Now,
my
if you
mind.
went to Jupiter and looked at the Jupiter moons, the
Planets
Jovian
orbiting the
moons, by the way, then they would also relate to each other, but by a different constant.
Wait, planets orbiting the Earth?
Planets orbiting the Sun would have a constant for the Sun.
Okay.
Planets orbiting Jupiter would have a constant for Jupiter.
Oh,
The Moon
okay.
and all of our satellites, including the astronauts, have a constant for the Earth.
Okay.
Okay? All right, now, you didn't know why, you just came up with those things. All right, so Newton comes along and Newton says, look, Fg equals negative big G m1 m2 over r squared. So this is Newton's big idea, gravity. Now, I don't know that you appreciate the momentousness of this idea.
I don't.
Do you think
Okay, because at the time, there were ideas of what were called natural forces, that things just naturally did certain things. Now, Galileo was the first one to kind of put the sword in that idea, but Newton came up with this even crazier idea that not only do things not have this natural motion, like for instance, they used to have this idea from the Greeks that light things would naturally float and heavy things would naturally fall. So that would mean if you took a rock and knocked a tiny piece off of it, then it should float. Now, actually, it does.
Yeah.
But we'll talk about that later.
If it's small enough, it will.
Actually, if it's small enough to be knocked around by atoms, it will.
Right.
And that's called Brownian movement.
Right.
Where if it's small enough, you can watch it in a jar of gas. You can't see the gas, but if it's small enough, you can see it get knocked around.
Or in your eye.
really thin and
had a lot of surface area.
Is that R just an average? 'Cause it's the-
Yes, that's correct. That's the average. It's the average of this and this, if I remember correctly. Okay. All right, now. Oh, wait, I never finished. All right, big G is 6.67 e to the negative 11 Newton meters squared per kilogram squared.
No. Why?
Because, now, Newton did not know what G was. Newton came up with this idea of force at a distance. Now, we take this for granted now because we have magnets and you have like two balloons that you can charge up by rubbing them on a cat and you can see the force between them. Okay? Now, the deal is that we take this for granted, but at the time, a force when objects don't touch was rather remarkable. And the only reason that people bought this idea was, one, because it worked, and two, because, yeah, Newton was famous and powerful, had powerful friends, and so kind of strong-armed a lot of people into believing it, because he had this aura about it. Okay, so like, all right, well, that's Newton's idea. We'll believe him, but we don't really believe it. Okay, but it worked.
Who had a bad
Okay, now, okay, here we go. Do this first. Here's the first thing you need to do. Force of gravity equals force of gravity. The force of gravity equals your weight. Okay?
Oh, that's too much.
Big G, M1, M2 over R squared, don't forget the negative sign, equals mg. Okay, here's the planet, here's you, you're M1, this is M2. So this is M1, your weight. Notice that your weight goes away, and you're left with that G equals negative, big G, M of the planet, over the radius between the center of mass and your center of mass. Well, your center of mass is so small compared to the planet, we neglect it. And this is just big R, the radius of the planet squared. Why negative sign? Because it's downward, because it attracts inward along the radius. The acceleration of gravity is in along the radius. But back up, everybody. This is not acceleration due to gravity. You silly, silly children. You've been calling this G the acceleration due to gravity all this time. Do you remember this? Electric force divided by charge equals electric field.
That's a G.
Yeah. Divided by charge. Sorry. But if I take gravitational force and divide by M, I get gravitational field. Because that's what we just did. And we call gravitational field little g. So even though you didn't know it, what we really have here, what we call meters per second squared, is really newtons per kilogram.
Oh my gosh.
Mr. Bruin.
That's gravitational field strength.
That's not.
Yes.
So technically, Yao Ming is more attracted to the Earth than Gia.
Huh?
No? You sure? What?
Well, yes, because he has more mass.
Who has more mass?
Almost everyone, Gia.
Yao Ming.
I'm a fighter.
Okay. Okay.
Are you serious? Is a really famous basketball
We
player.
did yesterday.
Yeah,
She's like,
I'm sorry,
girls.
but you're just not very attractive. You need more mass to be more attractive, young lady. She's starting to binge eat.
Oh my gosh.
Okay, everyone, this is gravitational field strength. G is gravitational field strength. Okay? That's what that really is. We'll come back to that a little later. All right. Blah, blah, blah. Now, that's right. Now, everyone, we can find this G because we can drop things and measure, right? The acceleration due to gravity.
That was a lab.
That's right. And we can find R for the planet. It's not that hard. Easiest way to do it was the way, easiest way.
More into the center of the earth.
Yes, right. bore into the center of the Earth, drop a string down, a measuring tape down.
We're sure it doesn't melt.
That's right. Make it out of some high temperature ceramic. The way a Greek, Egyptian, I don't remember. Somebody did it a long time ago. What they did is they had a well, and when the sun was directly overhead, it cast no shadow in the well, and then they had on that day their friend over here stick a stick up, and the stick cast a shadow. Okay? And from that information, knowing how big the shadow was, what angle theta it was here, and the distance between here, this theta equals that theta, voila, 360. So all they did is ratio the darn thing up, and they found the circumference of the Earth, and therefore found the radius of the Earth. Sweet. That's genius.
But wouldn't the long
I
be
don't
like
found the
a
mass of
specific?
The well has to be between the Tropic of Cancer and Capricorn where the sun could be directly overhead. Actually, the person who did this got a really good number. Really good.
Was it
All right,
like
so we know these two things. Here's the problem, though. We don't know the mass of the Earth, and therefore, what Newton's problem was is he didn't know what G was. Newton could not find G. All right? Newton could not find out what G was. So,
Who did?
Cavendish.
Who?
Oh, I think you said Kevin did. That was...
That's right.
Congratulations. Congratulations.
Kevin did. That's right.
Finally a normal name.
Cavendish did this.
Oh, Kevin.
Here's how Cavendish did it, everyone. He had two masses hung by a string,
Ew, it looks
a
like...
dumbbell, and then he had another big mass here and another big mass back over here, behind this one. And what happened is, if you look at it from the top, it did this. These were attracted and twisted, okay? And so what he did is he took a little mirror on here, shined a light on it. The light shined on the wall on a scale so that he could measure it. He knew how much force it took to twist the string, or the little metal wire. And from the amount of twist, he could measure backwards the amount of torque. And from the amount of torque, he could measure what gravity was. And so when he did that, he found out what G was, and by default, he found out what the mass of the Earth was.
Whoa.
Pretty sweet.